Um, so yeah, I'm gonna go ahead and get started, I guess. I know a few other people had said they were coming. And just remember that, whatever you're saying is gonna be on the recording. And so let's see, what kind of questions, I thought I would do the complex question first and let you guys follow along. You can write it down. You might want to get a calculator out. Oh, just realized.
Okay.
Reference sheet. And I'm going to publish this too, so that if you don't get it, you can watch it later. And then there's another video that does another one. So you have multiple chances to look at these kinds of problems, but this one will show you really what you should be looking at. Now, have you guys printed out this? Can you see this? The reference sheet?
Yes, ma'am, I have.
Okay. So when we do this complex problem, these are the three numbers you're going to need right here. The specific heats of, let's see, it says ice, water, and steam right there. Now this has specific heats of other compounds. And you'll notice that water is listed on there again at the very bottom. I don't want you to use this one, just use the one that's up here for water. But you can use these values right over here for all these other things. And the specific heat determines how quickly things heat up and how quickly things cool down. The other things you'll need is on this side of the reference sheet. And let's see here. Heat of vaporization comes first, and then the heat of fusion comes second. And then here are the compounds that it's dealing with and the formulas. So vaporization is where we turn it from a liquid to a gas, and fusion is where we melt it. We turn it from a solid to a liquid. So like you'll have to use both of these things, and you'll have to notice the units, which should be kilojoules over moles. You should be able to see that. Then the other ones you need, which I didn't do in the video yesterday, and I might do one today, is these are the heats of formation. So when it asks for a heat formation, you need to make sure you look on this big chart. Make sure you look for the correct phase, so solid, liquid, or gas. For instance, water is a liquid or a gas, and if you look at it, it's right here where I'm pointing. The liquid heat of formation for water is negative 285.830. Use all the numbers that are there, and the unit is kilojoules per mole. And for gas, it's negative 241. So if I ask you what is the heat of formation for water, you don't multiply it by how many moles are in the formula. Some people did that on the Ed puzzle. You just tell me what the heat of formation of water is. And so that's where you get the values, and the units up here, listed up here, kilojoules per mole. So it's pretty easy. And remember that all elements, the heat of formation is 0 because they're not formed. They're there naturally. But you can double check. Like phosphorus, I mentioned in one of the videos, and sulfur, sometimes they show up with like P4 and S8. Those are still just elements, so the heat of formation would still be 0. So the heat of formation is just the heat of the reaction to form whatever molecule you're dealing with. So we're going to do a complex problem first, and then we're going to do one of the heat of formation reactions. I'll pull one up from the homework and put it on there.
So you said the mole doesn't count for water. Is that what you're saying? If I'm doing this problem?
No, not the mole doesn't count for water. Just in the general equation, when we get there, the heat of formation is just the basic value. And then you can multiply that by how many moles you have. So, but when I get to that question, I'll show you what I'm talking about, okay? All right, let's start off with the complex problem first. And I'm going to give you basically an example problem and how it would be. So let's say we have 9.2 grams of water, and we're going to have it in, it's ice, so it's going to be, I'll just put this in parentheses, ice, because it's going to start out at a negative, let's say 8.7 degrees Celsius, and heat to all steam or water vapor, and we're going to go to 135 degrees Celsius. So I want to know how much energy it takes to do that. So we have this situation, and I want to know how much energy to do this. how much energy is required. All right, so the first thing you'll have to do for all of this is to draw yourself a picture. And I'm hesitant to get my eraser back out because I'm going to mess it up. So I'm going to draw a general picture. And we're going to label each part of the picture, okay? I'm turning my computer on because I'm also looking at my computer, my desktop, just for lighting and checking things. All right, now on this side over here is where you have the temperature in degrees Celsius. And then this axis, the x-axis, is where you're going to have your joules, which is your heat energy that's required. We start off way down here, and we're starting off at -8. Let me get -8 degrees Celsius, -8.7. Okay, Andrew, are you able to see this okay?
Yes, ma'am.
Okay,
yes,
awesome.
I see you.
All right, and then we're going to go up to the melting point of water. So that would be 0 degrees Celsius. You'll have to know that. You'll know that water melts at 0 degrees Celsius. And then we're going to go up to the boiling point of water. So that's going to be 100 degrees Celsius. That's a 100. And then we're going to heat that gas all the way up to 135. Okay, so what do we have down at this very bottom? We're starting off with 9.2 grams right there. And it's ice. And then we're going to heat this up. And in order to heat it up, I need this amount of energy. Now, the amount of energy we're talking about here is the joules from here to here. And the more joules that it requires, the bigger the specific heat would be. So this, water requires a good bit of energy to heat up. I explain all this too in the video that's open today that explains the Chapter 13 review Kia that you can look at. So we need this amount of energy to go from -8.7 to 0 degrees Celsius. Okay, so whenever you have a slope, whenever like this is where you're going to use the Q equals MC delta T formula. Those are the sensible heat areas. Sensible heat because you can detect a temperature change. You see it goes from -8 to 0. So there's a temperature change happening and you can detect it with a thermometer and you would be able to feel it. So those are sensible heats. You always use this. So in each place where there's a slope, like right there and right there, you're going to use this. Once I get to this spot, what I now have is 0 degrees water. I mean, it's 0 degrees ice. It's ice on this side. But on this side, it's going to be 0 degrees liquid water. So what happens between here and here is it melts. When it melts, the temperature doesn't go up. All the energy is being used to separate the molecules a little bit. So the melting is where you're going to use your delta H of fusion. So that's where you use that value. And so the formula for the delta H of fusion, and all of these are on your reference sheet right up here at the top. So you'll be able to use them. There's only one formula that's not up there, and I'll tell you to write it in a minute. So the delta H of fusion, you use it right here where the water melts. And then we get to this side and we have water, liquid. We have liquid water. We had ice down there, ice right here. It melts. Now we have liquid water. And now we're going to heat that liquid water up. And we heat it up from here to here. We're going to get something right there. Well, what we have there is 100 degree water liquid. So we just heated it up and we got hot water. So now what we're going to do from this spot to this spot is we're going to turn it to there, and it's going to be 100 degree steam or gas or vapor. All those are synonyms. So what we use in that spot then is the delta H, the heat, the change in the heat of vaporization, because vaporization is vapor, gas. So that's where we use that. And then we're going to heat it up again until we get up here and we have 135 degrees steam, because the phase changes only happen on the flat areas. Okay, so remember that. These flat areas are called the latent lazy heat areas, and that's where phase changes happen. It goes from a solid to a liquid, from a liquid to a gas. Are you following me on this so far?
Yes, ma'am.
Okay.
Yes, ma'am.
All right, we're going to calculate each amount of heat all the way through. So the first one, this is going to be Q1, not Q2. Q1 is MC delta T. All right, the M in this case always stands for mass. So M is mass in grams. It's not molality, it's not moles. And so we were given the mass of 9.2 grams. The C is the specific heat. And so you have to look at the state of matter. So right now we're ice. So if we look here, we can see the specific heat. Now let's see, it goes ice at the top. So right there, it's 2.05. Y'all see that?
I see it.
Okay, did you see it before? Yeah, okay, make sure you have this reference sheet. So 2.05, and it's joules per gram degrees Celsius. So this you get off the chart. And then the last thing is the delta T. And this is the formula that's not on your reference sheet, so you can write this down. Delta T is the final temperature minus the initial temperature. And it's going to be that for each spot. Okay, so let's look at our first one. For our first one, here's where we start. So that's our T initial. And then we heat it up, and that's our T final. So the final temperature and the initial temperature are for each step of the process. So for the first step of the process, the final temperature is 0 degrees Celsius, and the initial temperature is a negative 8.7 degrees Celsius. You follow me, guys, on that?
Yes, ma'am. And the 2.0, that's from ice, right?
The 2.05, it's from your reference sheet right up there, and it should say for ice.
Okay.
You got it? What I have highlighted in green is for the liquid phase of water. And so the ice is above it, liquid phase of water, and below that one is steam. Okay? So ice, water, steam. Ice, liquid, steam. Okay, so now we're just going to subtract these out. So 0 minus a negative is positive 8.7 degrees Celsius. We're going to cancel out our units. Grams in the numerator, grams in the denominator, grams in the denominator, grams in the numerator. The only unit that didn't cancel was joule. And let me pull out my calculator over here. Just multiply it through. 9.2, oh, it's not divided. Not, okay, 9.2 times 2.05 times 8.7. Double check my math. I got 164.08. Is that what you got?
Yes, ma'am.
All right, now we got to do sig figs. So 2 sig figs here. We don't count sig figs from a chart. 2 sig figs here. So the answer needs to be 2 sig figs. So we got to round to there. The 160 joules. That's the answer to Q1. That's how much energy it takes to heat the ice up from from a negative 8.7 to 0. Now we're going to calculate Q2, which is this amount of energy. How much energy is required now to melt the ice and get it from 0 degrees as ice to 0 degrees as water? So the new formula is the moles times the delta H of fusion. Now that is on your reference sheet, right here at the top. It's the one in the middle at the very top, okay? Right there. Okay, so I need moles, and I don't have moles, I have mass. So what do we have to do?
Compare it with the molar mass.
Exactly, you gotta calculate that molar mass of water, which we pretty much should have memorized by now, but we're gonna go through the process. I'll do it right over here. So water is H2O. So 2 waters and 1 oxygen times 1.01 times 16. You know you get these off the periodic chart. Add it all together, it's 18.02 grams per mole. Don't forget to multiply before you add. So now that's the molar mass, and I'm going to convert 9.2 grams to moles. So 1 mole is 18.02 grams. All right, so let's divide that out. 9.2 divided by 18.02, 0.510, 0.5105, and then significant figures again. So 2 significant figures. 1, 2, that is a leading zero. Leading zeros are losers. 0.15 moles. That's how many moles of ice I'm using. We're going to use that in 2 places anyway. So we put it up here for moles in that spot. 0.51 moles. And then I need the delta H of fusion. So I got to look on my chart for the delta H of fusion for water. Make sure you're looking at the right molecule. Okay, so the delta H of fusions are over here. And so for water, it is right there. And that's 6.01. So 6.01. And that is kilojoules per mole. Gotta write the right unit. All right, now we're going to cancel out our units, moles and moles, and figure out how many kilojoules it takes to melt this stuff. So 0.51 times 6.01, I hit 3.065, 2 sig figs, because this came off the chart. So that's where we're using our significant figures from. 1, 2, we round this to 3.1, and kilojoules did not cancel, so it's kilojoules. So that's our Q2. That's how much energy it takes to melt this ice. Are you following me okay?
Why does Q2 have a different formula than Q1?
All right, because Q2 is on the latent heat areas. Notice that Q1 has a change in temperature going from a negative 8.7 to 0. Mm-hmm. Q2, there's no temperature change. It's 0 to 0.
Okay.
All right.
Oh yeah, I see that.
Yeah. So it requires a different formula, and you have to use the heat of fusion and not the specific heat. Okay. All right. All right. You got that?
Yes, ma'am.
All righty. Now we're going to do to the next Q. This is Q3. In Q3, we're going to figure out how much energy right here it takes to turn it from a 0 degrees Celsius up to 100. So we're going from 0 to 100 now. So we're going to have a new T initial and T final. So the initial temperature in this area, we're going from, the temperature change range is going back up right here. Right there. So the initial temperature is down here now is 0 degrees Celsius, and the final temperature is 100 degrees Celsius. For every time when there's a slope, you're going to use, this is Q3, MC delta T. The mass is still 9.2 grams. All right, now we need the specific heat. Now, what state of matter is it in at this spot right there? What state of matter is that? What state of matter is it where I'm pointing?
Boiling?
Sorry, what? Is it a solid, liquid, or a gas right there?
Oh, solid.
No, it's a solid.
Oh, sorry, liquid.
Liquid.
Sorry,
it just
liquid.
got through melting. Right. It just got through melting, so it's a liquid. So we need the liquid specific heat value, the specific heat for liquid. Okay. So that's the second one. Uh-oh, I just dropped my calculator. Hold on. I'm back. So that's the second one on that list, and it's the 4.184. Okay. So 4.184 joules per gram degree Celsius. And then I need the temperature change. Well, the temperature change in this second section goes from a 0 to 100. You understand that? So the initial temperature is 0, the final temperature is 100 in this area. So T final minus T initial would be 100 degrees Celsius minus 0 degrees Celsius, which is just in 100. And we're going to put a decimal just so we don't lose all our significant figures. And I'm not going to be super picky about sig figs on this problem, but I do want you to show me what you're doing, because you're going to be doing a homework drop for these problems. Okay, now we got to cancel out our units. So let me change my color. Grams cancel with grams. Degrees Celsius cancels with degrees Celsius. My unit that's left is joules, and I just got to calculate it. So double check my math, make sure I'm putting it in correctly. I got 9.2 times 4.184 times 100. And I get 3849.28. Is that what you got? Hopefully. All right, I'm going to assume that's what you got. It looks like I put it in correctly. All right, sig figs. 2 sig figs, that came from the chart. 3 sig figs, we always take the smallest amount. So 2, 1, 2. So we're going to round to that spot. So it's 3800 joules. So that's Q3. Are you following me on that?
Yes, ma'am.
All right, Ivy, you okay?
Yes, ma'am.
All right, now we're doing Q4. All right, and that means we're going to figure out this energy. Now that energy is where we're going to go from a liquid at 100 degrees Celsius. We're going to turn it into steam or gas or vapor and go to vapor at 100 degrees Celsius. So that's where we use the delta H of vaporization. So Q4 then is the moles times the delta H of vaporization. And again, that is on your reference sheet. It's the third formula. Let's see, it's hard for me to point, and right around here, okay? All right, we've already calculated the moles, so we don't have to calculate it out again. We ended up with 0.51 moles. So 0.51 moles, and then I just need the delta H of vaporization. Does anybody have, if you have a reference sheet, tell me what the delta H of vaporization is for water.
It's 40.7.
40.7, good job. And kilojoules per mole. Moles cancel, and so we just got to multiply that through. So 0.51 times 0.51 times 40.7. And I got 20.76 or 20.757. I need 2 sig figs because that came from a chart. So this 7 causes the 1 to round up. So it's 21 kilojoules. Y'all follow me on number 4?
Yes, ma'am.
Yes, ma'am.
All right, good. All right,
Yes,
number
ma'am.
5. Okay, number 5 is this last part, Q5. And hey, Will, I saw you yesterday, so I'm going to do after this problem, I'm going to do another one. I don't know if you got to follow us through what this one yesterday, so just hang on.
Maybe not. Okay, sounds good.
What I'm going to do is one of the heat of formation problems after this. All right, so
Okay.
now we got to calculate Q5, which is from here to here. That's how much energy I need to figure out. So Q5 is going to go from 100 degrees up to 135 degrees. So I have now we have initial temperature is 100 and the final temperature is 135 because we're just going in this area. And we use, because we're changing the temperature, the only formula with a change in temperature is that one. So Q equals MC delta T. The mass is still 9.2 grams. But now I need the specific heat of steam instead of water, liquid, or water as an ice. So one of you guys tell me what the specific heat of steam is off your reference sheet, and I'll double check, make sure you're looking at it correctly. Ivy, can you look at, do you have your reference sheet in front of you?
I'm pulling it out right now.
Okay.
I'll grab mine too.
Yeah, because we're going to need, I want y'all to have them out for the next question anyway when we do a heat of formation question. Okay, what you got, Ivy? Specific heat of steam. That's what I'm looking for.
Oh, one more second. I think I moved it in a different place.
Okay, Will, do you have it then?
Yes, ma'am. Is it 2.01?
Correct. 2.01 joules per gram degree
Per gram.
Celsius. All right, now we need the delta T, which is T final minus T initial. All right, so the final temperature here is 135, because that's where we went to. The very final is 135. And the initial temperature is 100. Now, do y'all understand why that's like that? It's only the temperature change in the range that you're dealing with, okay? It's not the temperature change of the whole spot. It's only the temperature change when you change it from from steam at 100 degrees to steam at 135. So every temperature change only deals with its section. Okay, so we subtract that out, we get 35 degrees Celsius. And now we just cancel out our units. And then degrees Celsius in joules is my only unit. And let me pull up my calculator, or use my calculator. So 9.2 times 2.01 times 35, I get 647.22. And I got 2 sig figs because that came from a chart. So goes to there. 7 causes the 4 to round up to 650 joules. That's all 5 of them, okay? So now the question really wants to know how much is all of this energy from this side to this side. So we just add each one of them together. So the total energy, the total Q, is going to be each Q added together. So Q1 plus Q2 plus Q3 plus Q4 plus Q5. Q1 is 160 joules. Q2 is 3.1 kilojoules. Q3 is 3,800 joules. Q4 is 21 kilojoules. And Q5 is 650 joules. Now, you can't add these immediately because we have to have the same units to add. So I'm going to turn the kilojoules into joules. And I could have turned the joules into kilojoules, but turn the kilojoules into joules just because there's only 2 of them to convert rather than 3, okay? So 3.1 kilojoules. You have to remember there are 1,000 joules in a kilojoule. Cancel that out. So you're just going to move your decimal place 3 places, 3.1123. So that's 3,100 joules. So instead of using this, I'm going to write 3,100 joules. And then for the 21 kilojoules, it's the same process. Kilojoules cancel, so it's 21,000 joules. Now, just a side question, that means Q4 requires the most energy. So it requires the most energy then to turn it from a liquid into a steam. You see that? Everything else is less energy. Now all I got to do is add all these things together. 160 plus 3,100 plus 3,800 plus 21,000, 1, 2, 3, plus 650. It will be a big number, 28710. And significant figures. You remember when you're adding, you look at precision. So this one only goes to the thousands place. This one goes to the thousands, but it goes to the hundreds. This is the least precise number, so we have to go to the thousands place. And so we round it. The 7 causes the 8 to round up to 29,000 joules. Final answer. Okay, guys, this question, notice how much work is here. You're going to be required to draw me this picture. You have to write all the formulas that you use and then substitute and then solve. You have to convert your, do the molar mass and convert it to moles. And then you have to, once you do all that, you know, change the kilojoules to joules, then add it all up. There's a lot of places to make mistakes. So it's very important that you show me your work carefully so that I can evaluate for partial credit. I won't be super picky with sig figs, but I am going to be picky about things like you need to write the formula every time. This is what I mean so that's 1, 2, 3, 4, 5 formulas. That's 5 points right there, okay? And then you do all the work. You got 1, 2, 3, 4, 5 answers, 2 conversions, a final answer, a molar mass, a moles, and a picture. All that's the points for all of this. So I would just want you to notice how many points this one question has.
Thank you, Ms. Cribb.
Okay. All right.
I'm going to leave and go to Ms. Johnson's class. I'll catch you later.
No worries. I'm going to put this up when I get done, okay?
All right, thank you.
All right. Now what I'm going to do is erase this one and do a heat of formation question. I apologize. So 2C2H6 gas plus 7O2 gas yields 4 CO2 gas plus 6 waters liquid. Okay, this one was on the video, and you had to put in the values and then calculate it out, and there's some errors with this one anyway. So I'd like to do this one, calculate the heat of the reaction. It's still going to be, the heat of the reaction is going to still be the heat of the sum of the heat of the products minus the sum of the heat of the reactants. And then C2H6 gas. So if I look on here for C2H6 gas, okay, that is on the, I'm making sure all the values are actually on what you have. There, it's listed on this first column. So C2H6 is negative 84.68. So we're looking at the delta H of formation from the chart. And that was negative 84.68 kilojoules per mole. Water is still 0 kilojoules per mole. Carbon dioxide gas is also in that first column, negative 393.509 kilojoules per mole. And then liquid water is in the second column on that green chart, and it's negative 285.830 kilojoules per mole. All right, do you guys understand where all these values are coming from here?
Yes, ma'am.
Okay, awesome. Now notice I did not multiply them by the moles yet. I just put the value from the chart. That's all that's asking for. What is the heat of formation for that thing? Now we're going to add all the products up. This is the product side. So no matter what the reaction is that I give you, I did make sure on the test that all the values are in that green chart. This is the product side. So you always add the product side up first. So now this is where you concern yourself with the number of moles in the question. So it's 4 moles times this, negative 393.509 kilojoules per mole. Plus, because that's what this means. It means that's a summation sign. You add them all up. Plus, we have 6 moles of water. 6 moles times negative 285.830 kilojoules per mole. All right, that's the product side. And then we're supposed to subtract, so I'm going to write a negative, the sum of the reactant side. So this is the reactant side. All right, so now we get the same process. There are 2 moles of this stuff. So 2 moles times the value you got off the chart, negative 84.68 kilojoules per mole. And then we have to add it because this means add. These little signs mean add. So add 7 moles of oxygen. Well, I mean, I'm going to write it in there, but it's 7 times 0. So 7 moles and 0 kilojoules per mole. Okay, I want you to notice again, and this is the common error. It's the product side minus the reactant side. People a lot of times reverse it. They just add this up and subtract out this side, and they get the opposite answer. So make sure you do products minus reactants. All right, cancel out your units all the way through. Moles go away. This completely goes away because of the 0. Multiply 4 times a negative 393.509. Negative 393.509 times 4. So this would be negative 1574.036 kilojoules plus 6 times this number, 6 times a negative 285.30. So plus, let's go negative 1714.98 kilojoules. And then we got to put the minus sign between the two sides. Minus 2 times this, 2 times 84.68, but it's negative. Negative, because of that, see? Negative 169.36 kilojoules. All right, you follow me so far, guys? Ivy, you doing okay?
Yes, ma'am.
All right, now you got to make sure you subtract the negative. So now we're just going to do the math. We're going to add these two together because we're adding. So negative 1574.036 plus a negative 1714.98 gives me a negative 3289.016. Subtract. What are we subtracting? A negative 169.36. And all of this is kilojoules. Both of them are. Now I just should be able to do the math. Subtract the negative 169.36, and I get a negative 319.656. And if I look in significant figures, I have to end there. So negative 319.66 kilojoules. This is the heat of the reaction, the delta H of the reaction. It's also the heat, if you calculate the heat of formation, the heat of combustion, all of them use the exact same formula. The only difference is heat of combustion just means you're dealing with a combustion reaction. Heat of formation just means you're dealing with a synthesis reaction. You're just putting things together, okay? But every single one are calculated exactly the same way. Y'all follow what I did?
Yes, ma'am.
All right, now let's notice that it's negative. So is this an endothermic or exothermic reaction? What do you think? Do the products have more or less energy than the reactants? Well, if the change in the heat is negative, every time it's negative,
It's exothermic, right?
Exothermic.
Yeah.
It started off with reactants way up here. They lost a bunch of energy, and now their products down here. So between here and here, that's your change in your heat. If that's a negative value, it's exothermic. So an exothermic reaction always has the products below the reactants. If this was a positive value, the opposite reaction, you start off with reactants, you go up, and here have products on top. That delta H would be positive, and that would be an endothermic. So this is an exothermic because it's negative. You follow me? You all got that?
Yes.
Okay. All right. Are there any other questions I can help you with today? All right. Well, we're going to end the session then, and I'll send this recording out to everybody so that you can review if you need to, okay?